All right, diving into some cutting-edge AI research today. I know you're going to love this one.
Oh, yeah.
Yeah, we're breaking down this paper called Experience Replay with Random Reshuffling.
Nice.
You know how you're always looking for those ways to just make RL training smoother, more efficient?
Always chasing that stability.
Exactly. Well, this paper, they're basically taking this idea, random reshuffling, something that's been like a workhorse in supervised learning for ages.
Oh, right.
And they're seeing if they can bring some of that magic over to the world of reinforcement learning and experience replay.
Interesting.
So they've got these two new techniques they're introducing, RRC and RRM.
Okay.
RRC is all about reshuffling the indices in a circular buffer for uniform replay. Kind of clever, right?
Yeah, I'm curious to hear more about that.
And then RRM that uses this masking technique based on how often things get sampled to try and bring that same kind of balance to prioritize replay. And get this, they actually ran experiments on Atari games, and they're seeing some pretty solid, consistent performance boosts when they use these methods with algorithms like DQN.
Very cool.
Yeah. So basically, the big question they're wrestling with is, can we take what we know works so well in supervised learning, this random reshuffling thing, and actually make it work in the crazy world of reinforcement learning and its experience replay?
Right, because experience replay is so fundamental to how we do deep RL now. You know, it's kind of a big deal if you can improve that.
Absolutely. And that's what we're here to unpack today. You know, see what's really going on under the hood with these new approaches.
Yeah.
See why they work, what the implications might be, and what it could mean for anyone out there building AI.
Awesome.
All right. So first things first, let's set the stage. What's the problem they're even trying to solve here with traditional experience replay? Why explore this new approach at all?
So at its core, it's about how we sample those experiences from the replay buffer, right? The way most deep RL implementations do it now is they sample transitions with replacement.
Okay.
Which has been a huge success, don't get me wrong, but it inherently brings in this variance in terms of how much each experience actually gets used in training.
Right. Some get picked a ton, others get left behind.
Exactly. Some transitions might get picked over and over again, while others just kind of sit there in the buffer, barely contributing to the learning.
And the paper points this out, right? It's like the complete opposite of what we do in supervised learning.
Yeah, in supervised learning, random reshuffling is basically the gold standard. You shuffle the whole data set at the start of each epoch.
Right.
And then every single data point gets looked at just once during that epoch, and there's solid theory behind why that works so well for convergence.
And it makes sense, gives the model a chance to see everything equally.
Right. Exactly. Every data point gets its fair share of attention, helps prevent the model from getting fixated on just a small part of the data, leads to that more stable, often faster convergence, especially with certain loss functions.
So how do we take that and bring it over to RL?
See, that's the tricky part. The paper hits on this really important difference. Supervised learning, it's got this fixed data set. It doesn't change.
Static.
Exactly. But in RL, that replay buffer, it's constantly evolving. It's a dynamic beast.
New experiences coming in all the time.
Exactly. New data flowing in as the agent interacts with the environment. And then you add prioritized experience replay into the mix.
Right, where the importance of each experience can change as we learn.
Yeah, so it's not just that the buffer's changing. The importance of what's in there is shifting too. So just trying to do a direct copy-paste of the supervised learning approach, it just wouldn't work, wouldn't address those underlying issues of sampling variance and using data efficiently.
That's the gap they're trying to bridge, right?
Exactly. That's the challenge these researchers are taking head on.
Okay, let's get down to brass tacks. Walk me through their first method, the one specifically for uniform experience replay, RRC.
Okay, so RRC, random reshuffling with a circular buffer, they're aiming to bring those same random reshuffling advantages we talked about, like basically ensuring every data point gets its fair share and that new data gets a chance to uniform experience replay. And their big insight here, and this is what I think is so neat about it, is they apply the random reshuffling not to the actual experiences themselves, but to the indices that point to those experiences in the circular buffer.
So instead of shuffling the memories themselves, they're shuffling the pointers to the memories.
Precisely. Think of it like this. Imagine your replay buffer is this ring, right? Where new experiences kind of push out the old ones in a cycle.
Like a carousel almost.
Yeah, exactly. So at the start of what they call an epoch, and this is important, it's not a training epoch in the usual sense, but one full pass through their shuffled list of indices, they create this randomly shuffled list of all the possible indices in that circular buffer, from 0 to however big the buffer is, -1.
Okay.
And then whenever the system needs to sample a mini batch of experiences to train with, it just goes down this shuffled list of indices one by one.
So instead of grabbing experiences randomly, they're grabbing these shuffled pointers.
Exactly.
What happens if they grab a pointer, an index, that points to a spot that's been overwritten? Like the experience that was there is gone, replaced with a new one.
Yeah, that's a great question. And they address that directly in the paper. They say if a sampled index points to a spot that's been overwritten, they just skip it, move on to the next one in the shuffled list.
Makes sense.
So the big win with RRC, the key advantage, is that across one of these epochs of shuffled indices, every single index in the buffer is guaranteed to be considered for sampling just once.
So it really evens out the playing field for those experiences, right?
Exactly. It levels out how often different experiences get used to train the model over the whole training process. And from a computation standpoint, it's super efficient. Shuffling a list of numbers is way faster than shuffling a massive amount of data objects.
Right.
Plus, the authors point out, no new hyperparameters to tune, always a win.
Sounds pretty slick. So that's for uniform replay. What about prioritized replay? That's where RRM comes in, right?
Yeah, RRM, random reshuffling by masking. And this is where things get a bit more intricate because now we're dealing with the added complexity of those priorities changing all the time.
Because the importance of an experience can go up or down.
Precisely, and that's updated often after a transition's been used in training. So trying to do that clean one pass without replacement sampling, like in supervised learning, with a static data set becomes much harder.
So how does RRM handle that constantly shifting priority landscape?
Well, it takes a different approach than RRC. Instead of focusing on how things are accessed, it tackles the issue of oversampling those high-priority transitions head-on.
Okay.
It keeps track of how many times each transition in the buffer has actually been sampled during training, and it compares that to how many times it should have been sampled based on its priority.
So it's looking at the actual sampling versus the expected sampling.
Exactly. It maintains an actual count and a calculated expected count for each transition.
Gotcha. So what happens when a transition gets sampled more often than it should based on its priority? That's where the masking comes in.
Got it. When a transition is considered oversampled, meaning its actual count has gone above its statistically expected count, based on its priority, it gets temporarily masked. They essentially set its priority to a very small value, so it's much less likely to get picked again for a while.
So it puts the brakes on those popular experiences, gives others a chance.
Exactly, until that expected count catches up.
What about within a mini batch? How does the selection work there with the masking in place?
So within a mini batch, sampling is still guided by the priorities, but the key is it's using the masked priorities.
So transitions that haven't been oversampled are much more likely to get picked.
Exactly. And the paper also details how they handle those situations where old transitions in the circular buffer get overwritten by new ones. They reset both the actual and expected counts for those overwritten transitions.
Okay.
And then they rescale the expected counts for all the remaining transitions so the probabilities stay consistent for sampling.
So there's definitely more bookkeeping going on here compared to RRC, more computation. And they mention in the paper an ON cost for updating those counts and being the buffer size.
Yeah, and that can be a real concern, especially for those really huge replay buffers we often see in deep RL.
Could get expensive.
Absolutely. Keeping track of those actual counts, it inherently means knowing which transitions got picked in each mini batch, which is O batch size.
Right.
But the more intensive part is updating those expected counts, which naively could mean going through all in transitions in the buffer, hence the ON. But the authors, they recognize this potential bottleneck, and they talk about using GPUs and libraries like CuPy to parallelize things efficiently. They also suggest using two sum trees, one for the original priorities and one for the mask priorities, which can bring those priority updates down to OB log n, where B is the batch size.
Okay.
And they even float the idea of approximating things, updating less frequently to save on computation.
Interesting. So there's definitely some trade-offs to think about with RRM, especially with those mega-sized buffers. But let's talk about the results. They did a bunch of testing on the Atari Benchmarks, right?
Yeah, they started with some simulations, kind of simplified scenarios with experience replay, just to isolate how RRC and RRM affect the distribution of those sample counts.
So a controlled environment to really see what's happening.
Exactly. And these simulations, they showed pretty clearly that both methods were really good at reducing the variance in how many times each transition got sampled.
Compared to the usual with replacement method.
Yes, and even compared to a basic without replacement approach, so For uniform replay, RRC gave them a much more even distribution of samples, and for prioritized replay, with those priorities changing, RRM successfully reined in the tendency to oversample those high-priority transitions.
Okay, and then they moved on to the real deal, the full deep RL experiments.
Right, so for uniform replay, they focused on a subset of 10 Atari games, good mix of challenges there.
Yeah, solid benchmark.
Yeah, and they looked at how well-known algorithms like DQN and C51 performed with and without RRC.
And what did they find?
It was pretty promising. In most of those 10 games, both DQN and C51, when they used RRC, they consistently outperformed their baseline counterparts that were using the regular with replacement sampling.
So using RRC gave them a performance boost.
Yeah, and while the size of the improvement in each game, it wasn't massive, the fact that it was consistent across different games and across different RL algorithms, it really suggests that RRC is doing something beneficial, helping the system learn more effectively from those past experiences.
I also noticed they tried a within MiniBatch without replacement sampling method for uniform replay, and it didn't really improve things compared to the standard with replacement approach.
Right, and that's interesting because it tells us the main benefit of RRC isn't just about avoiding duplicate samples within a MiniBatch.
Yeah, it's got to be about that bigger picture, the buffer level balancing over the whole training process.
Exactly. Those replay buffers are typically huge compared to a single MiniBatch, so the chances of picking the same transition twice in the same MiniBatch, even with replacement, are pretty slim. It's RRC's ability to ensure that more even distribution across the entire buffer over time that seems to be making the real difference.
Okay, let's talk prioritized replay experiments. They use DDQN with the LAP extension, right? On the same Atari games.
That's right, DDQM plus LAP, and again, they were looking at the impact of adding RRM into the mix. Well, similar story to the uniform replay experiments, RRM showed performance gains. In 8 out of the 10 games, the DDQN plus LAP agent with RRM did better than the baseline agent using standard with replacement sampling.
So even with the added complexity of those priorities changing, RRM still made a positive difference.
Yeah, again, the performance differences weren't huge in every game, but the overall trend definitely points to RRM successfully bringing some of those variance reduction benefits to prioritized replay.
They also compared RRM to stratified sampling, right, which is another technique sometimes used with prioritized replay to get a better mix of experience ages.
Yeah, and this is where it gets really interesting. They found that combining RRM with stratified sampling, they called it RRM plus ST, actually outperformed stratified sampling on its own in 8 out of the 10 games.
So even when you're already trying to ensure a mix of old and new experiences, RRM's focus on balancing based on priority still adds value.
Exactly. It's like they're complementary. Stratified sampling is all about age diversity. RRM is about priority-based sampling frequency. And together, they seem to work really well.
They also talk about related work, mentioning methods like combined experience replay, CER, and corrected uniform experience replay, CER. How do RRC and RRM compare to those?
Right. So the authors point out that while methods like CUR, which always includes some recent transitions in each mini-batch, and CUR, which dynamically lowers the priority of frequently sampled transitions, they all share the goal of reducing variance and potential bias in experience selection.
Right.
But RRC and RRM, they're more direct in how they tackle that unnecessary variance. RRC guarantees each index in the buffer gets considered exactly once per epoch, and RRM actively monitors and masks those oversampled transitions.
So more of a proactive approach.
Yeah, and unlike CUR and CUR, they don't inherently favor recent experiences, which can be good or bad depending on the RL problem, makes them potentially more broadly applicable.
Yeah.
They also mention that many other experience replay extensions, like hindsight experience replay, could be combined with RRC or RRM for even better performance.
Cool. So to wrap this up, what are the key takeaways for our audience, the AI folks out there?
Well, the big one is that this idea of taking random reshuffling from supervised learning and applying it to RL's experience replay, it's a really promising direction.
Okay.
RRC, it's a simple but effective and efficient way to improve uniform experience replay, making sure those past experiences are used more evenly.
Right.
RM, it's a clever way to bring those same benefits to prioritize replay, handling those dynamic priorities and preventing oversampling.
And they actually work in practice.
Yeah, the results they got, while not always huge jumps, were very consistent across different Atari games, different RL algorithms, and that points to real practical value, not just some niche improvement.
Right.
And importantly, both are designed to be easy to integrate into existing systems. They're drop-in replacements for that standard with replacement sampling.
That's huge for adoption.
Absolutely. Plus, they've made their code available on GitHub so people can try it out themselves.
Nice. Any caveats, things to watch out for?
Yeah, gotta keep in mind that potential computational overhead with RRM, especially with massive replay buffers, that ON update cost can be a limiting factor.
Right. So this whole deep dive, it really highlights how borrowing ideas between different areas of machine learning can lead to some really cool innovations.
For sure.
The idea of using past experiences more evenly, whether uniformly or based on priority, it just makes sense intuitively for building more stable, more efficient RL agents.
Absolutely.
And the consistent performance gains they showed, even if small in some cases, across those Atari games and different algorithms, it tells us these aren't just theoretical concepts, they're tools ready to be used.
Yeah.
And the fact that they're relatively easy to implement, it's huge. The thorough experiments, the comparisons to other methods, it all makes a strong case for RRC and RM. So hopefully this breakdown has given everyone a solid understanding of what's in the paper, what it means for their work. It's a prime example of how cross-pollination of ideas in machine learning can lead to real breakthroughs.
It is.
Now, I'm curious, what parts of this resonated most with you? Can you see yourself using RRC or RRM in your own projects?
Yeah, that's a good question. I'm thinking maybe.
We'd love to hear your thoughts, and we encourage everyone to check out the full paper, maybe even try implementing these methods themselves.
Yeah, definitely worth exploring.
The fact that we're still seeing new and improved ways to do experience replay, it just shows how much potential there is in this area, how much more we can do to build better, more powerful AI.
Absolutely.
And that's a wrap of this deep dive. Thanks for joining us.
Thanks, everyone.